Today's topic is general row echelon form. So far, we've been focusing on mainly square matrices, n by n matrices, which in terms of linear equations corresponds to having the same number of equations as variables, or unknowns. So let me just remind you, if you have a 2 by 2 equation like this, then, well, the number of rows is the number of equations, in this case 2, and the number of columns is the number of knowns, in this case 2, which are x and y. And I want to turn next to a situation where these aren't equal, so we're talking about m by n matrices. So let's just look at a very simple example. You have a 2 by 3 system like this. Suppose I gave you this matrix equation. This has two equations, and that is to say 2x plus 3y plus z is equal to 7, and x plus 2y plus 4z is equal to 8. And there are three unknowns, x, y, and z. So this is a 2 by 3 matrix, two equations, three unknowns. So what's the strategy for solving such a system? Well, it's very much the same as what we were doing for square matrices. It's Gaussian elimination. And what happens? You have this equation ax is equal to b, and what you do is you apply a bunch of row operations, which means operating on the left by a matrix L, and you replace this with the equation L ax is equal to b, where, say, L is special or triangular. Or another thing you could do is you could apply a permutation matrix on the left and get this, and you keep going, and well, you try and use these operations to put A into a nice form. Well, what form would that be? In the case of a square matrix, we were trying to make it upper triangular. Well, that doesn't quite make sense for an arbitrary size matrix. So let's think about that for a second. So this is what we tried to do in the case of a square matrix. You put it in upper triangular form. And what replaces this for a general n by n matrix is what's called row echelon form. So let's look at what that is. So we start with our matrix A, and we try and put it into the following form. We try and have a non-zero number here, that is to say a pivot, which I'm circling in red, and everything below that is supposed to be 0. And there might be some extra zeros down like this that come along. And then you have another non-zero pivot, which I've circled here. And then everything below that is supposed to be 0. And you have a staircase phenomena like this. And the picture is that you want to get the matrix into this form, where the first non-zero entries in each of these rows are indicated as such, and then those are the pivots, and then everything below that is supposed to be 0. So this is the definition of row echelon form. It's like this, where each of the pivots is non-zero. Everything in a row after a pivot you don't care about. That could be anything. But everything below a pivot and to the left of any pivot has to be 0. So the pivots are non-zero, and everything below the staircase, so to speak, is required to be 0. And I don't care at all what's about the rest of the matrix up top. So that's the definition of row echelon form. And there are 2 points about row echelon form. The first is that if you have a matrix equation where the matrix is in row echelon form, it's very easy to solve. So this is a worthwhile destination. If you get a matrix into this form, you'll be able to solve the equation you were trying to solve. So that's good. And the second thing is you can always do this. Any matrix can be put into row echelon form by a series of row operations. So that pretty much completely, in a nutshell, this tells you how to solve any matrix equation. You put it in row echelon form as you can, and then it's easy to solve. So let's look at an example. So here's an example of a matrix equation where the matrix is in row echelon form. It's a 4 by 6 matrix, that is to say 4 equations and 6 unknowns. And the matrix is in row echelon form because this 2 is a pivot, and the 1 and the staircase looks like this. 2, 1, and 1 are the pivots. Everything below those and to the left of those is 0. And I want to illustrate, first of all, why this is good. It's easy to solve this equation. So the first thing you do is you label these pivot columns. I'm just going to label them in red for the moment. And the other columns are different. I'm going to label those in blue. Those are called the free columns. And these correspond to the variables. And so this x1, x3, and x4, the ones corresponding to the pivot columns, and x2, 5, and 6 are the free variables corresponding to the other ones. So you say that x1, x3, and x4 are the pivot variables, or sometimes called the dependent variables, whereas variables x2, x5, and x6 are the free variables in this example. And the point is that you can set these 3 free variables to be whatever you want, and then the pivot variables will be completely determined. The x4, 2, 5, and 6 can be anything, and then you're done. That determines the pivot variables if you're trying to solve this solve this equation. So why is that? So one of the third equation that you get, the non-zero equation that you get here, if you write it out, says x4 plus x5 plus x6 is equal to 5. Well, x4 is a pivot variable, so and the other two are free, so you move those to the other side and you solve and say x4 is equal to x5 minus x5 minus x6. And then you go back to the previous line and you write out the equation that gives you. And again, you have a single pivot variable here, and you bring the others to the other side, and you conclude that x3 is 8 minus x5 minus 4x6. And then finally you go back to the first row and you write 2 x1 plus x2 plus x4 plus 2x5 plus 3x6. All of that's equal to 13. And you bring everything to the other side, and you have x1 is equal to 1/2 of 13 minus blah, 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 all the other stuff. And now all of these things on the right-hand, not all of these things on the right-hand side are free variables. The 5 and the 6 and the 2 are. But that's okay. We're doing back substitution. So the one other one that's not free is this x4. There's x2. I have this x4 here, and that's fine. I know from 2 lines up how to solve x4 in terms of x5 and x6, so I just plug that in there. And that gives me a formula for x1 in terms of just the free variables x2, x5, and x6. So that's how you solve an equation once it's in row echelon form. The conclusion is that you can set x2, 5, and x6 arbitrarily, and then these equations tell you what x1, x3, and x4 must be. So here's another example. I'll work this one out a little more. We have this row echelon form and this 4 by 5 system. And I have 3 pivots here. That's variables x, z, and w. And the free variables are y and u. And so to solve this, I look at the last non-zero equation, and I get w plus u is equal to 2. And let's see now. W is a pivot variable, and u is a free variable. So I write w is equal to 2 minus u, and I don't have to, I'm done with that. And then you go back to the previous line and get z plus 3w plus 2u is equal to 6. And let's see, z is a pivot variable. W is also a pivot variable. U is free. Anyway, you write z is equal to 6 minus 3w minus 2u. And now you look at the right-hand side of this. U is fine. That's free. W, sorry, 6 is just a number. W is not a free variable, so you have to do back substitution, plug in for it. 6 minus 3 times 2 minus u, minus 2 times u, and now everything's in terms of u, and you get, you just work it out. It turns out to be u. So I've just solved for z in terms of u and y. It's just z is equal to u. All right, and then you go back to the very first equation. X plus 2y plus z plus w plus u is equal to 6. And bring everything but the x to the other side. X is equal to what? X is equal to 6 minus 2y minus z minus w minus u. And the y and the w, excuse me, y and u are free, and the z and w I know from back substitution. Let's see, the z is equal to u from this line one above, so I plug that in, get minus u, minus, let's see, w is from, let's see, that's the first thing I did, it's this 2 minus u, so I plug that in here to get 2 minus u. Minus u, and now everything on the right hand side is y's and u's, and so I've solved, and if you work it out, it turns out that x is equal to 4 minus 2y minus u. So there's x, there's w, and I'll rewrite z up over here, and z all in terms of u and y on the right-hand side. So you can set u and y to whatever you want, and then x, z, and w are determined. So for example, if you wanted to find a solution to this equation, you could take, let's say, u is equal to y is equal to 1, say. I wrote w here, that's a misprint, it's y. And then if u is equal to y is equal to 1, you conclude that w is equal to 2 minus 1, which is 1, and z is equal to 1, and x is equal to 4 minus 2 minus 1 is equal to 1. So you get the solution 1, 1, 1, 1, 1. There are other solutions, infinitely many in fact, we'll be talking about that, but there's one possible solution. Okay, so we've seen that row echelon form is good. Now let's do the other part of the program. The theorem is that if A is any m by n matrix, then it can can be reduced to row echelon form by a series of row operations of the usual type, corresponding to lower triangular and permutation matrices. Any matrix can be put into row echelon form by these familiar operations. And another way to say it is that any matrix can be, if A is any matrix, you can find P, L, and U such that PA is equal to LU, where U is now in row echelon, L is special lower triangular as usual, and P is a permutation matrix. Or, as usual, you could put the L on the other side, and you could say that LPA is equal to U. And that's, in terms of running the algorithm, that's slightly more convenient, what we tend to do. So let's sketch why this is true, and that is to say, give the algorithm. That's what it amounts to. So here's how you do it. Well, you look in the very upper left-hand corner of the matrix, and let's say for the sake of discussion that the upper left-hand entry is non-zero. It's a pivot. So you circle that. It's a pivot, and you use it to kill everything below. You use it by adding rows going down, you can make everything below it equal to 0. That's the usual thing. And let's see, what happens next? Well, so you've modified the rest of the matrix. It may be that when you look at the second column, you might already have a bunch of zeros there. You might or you might not, but it's possible you do. So let's say, for example, that that happened, that I don't care about this very top entry, but suppose everything down here was 0. That can happen. This is the pivot. But typically, let's say, for example, you then look at the next column, and maybe the entry in the second row of the next column is non-zero. So let's suppose that the next entry is non-zero. I'll label it here. If that's non-zero, then you can use that to kill everything below it. And you're working from left to right. The matrix is getting into row echelon form. So you do this, and then again, maybe you look one column to the right, and maybe it has some zeros, maybe it doesn't. Let's say you got some extra zeros for free here. And now you go finally, let's go to another column, and now the one thing that could be different is that you have an entry 0, but then a non-zero entry below it. And that's not good. You can't kill that entry by using a pivot, because you don't have a pivot to use, and so this is where you do a permutation. If this happens, you just permute to put that red pivot up where it belongs, and then you continue on your merry way. And when you're done, the matrix will be in row echelon form. So I've written it here like this. You flip like this, and if there were other non-zero entries, of course, you could use this pivot to kill them. So that's a sketch of the algorithm. Let's do an example. Here's a fairly typical 4x5 matrix. So this number is non-zero, so we can use it to kill everything below it by multiplying by -2, -3, and -1 as usual to kill all the entries below it. And when you do that, you get to this matrix. Now let's see, you get 0, 0, what do you get here? 1, 2, 1. And then here you get a 0 and a 0. And let's see, you get 1, 2, 2. And then when you add to the bottom, this is what happens. So notice that in this case, we got an extra an extra column of 3 zeros for free. And we keep going, and we look one column over. Here's a non-zero pivot. We can use that to kill everything below it. And what happens when we do that? Well, let's see. The first two rows stay the same. And the next thing that happens is I kill everything below this 1. And when I do that, this is what happens. I get 0, 0, 0, 0, 1, and then this becomes this. And okay, so I've taken care of this pivot and this pivot, and I look one column to the right, and now there's trouble because I have a 0 above a 1, and I need to permute to fix that. So now you apply a swap of those two rows, and you get to 1, 2, 1, 1, 1. Let's see, 0, 0, 1, 2, 1, 0, 0, 0, 1, 3, and 0, 0, 0, 0, 1. And now it's in row echelon form. So here are the 4 pivots. This last one down here is a pivot, and there's my staircase, and that's an illustration of the algorithm. Okay, here's a very important definition. If you have a matrix, not necessarily square, the rank of the matrix is the number of pivots that arise when you put it in row echelon form. The number of pivots, and remember, pivots are by definition non-zero. Another way to say it is the rank of a matrix is you put it into row echelon form, and it's the number of non-zero rows once it's in row echelon form, because every non-zero row has a pivot. So the number of pivots is exactly the same as the number of non-zero rows. Okay, so let's go back and think about this a little bit in the case of an n by n matrix. So let's look at the following example. Suppose A is n by n, and I ask that what does it mean for the rank of this matrix to be n? So how can you have n non-zero pivots? How can this thing have rank n? Well, let's see. This first guy must be a pivot. The row echelon form has to be this. It's got to be a staircase with all steps and no horizontal, no extra columns of zeros, so to speak. And the steps are all along the diagonal, and all of these AIs are not, they're pivots, so they're non-zero. And that is to say, that's exactly the requirement that the matrix be non-singular. So this is a very important fact. This is another property of non-singular matrices, so I'll state this as theorem. If A is an n by n matrix, it's non-singular. Remember, that means it's invertible. If and only if it has the rank is n, which is to say the rank is as big as possible. It's it can't be any bigger than n. So okay, so let's look at a couple of examples of the ranks of matrices. So let's see. Let's take this 3 by 3 matrix. And what's its rank? Well, unfortunately, you can't just glance at it and tell. You have to run the algorithm. So you run the algorithm. There you go. You kill the 0 by adding -1 like this, and then you add -2 like this, and you get this. And then you do another step of the algorithm, and you use the second row to kill the third row. And what do you know? You have a row of zeros. So there's only 2 pivots. This last 0 is a 0 and not a pivot. So the rank of this matrix is 2, and it's not invertible. This is a singular matrix. Okay, let's look at another example. Let's take not a square matrix, but the following matrix. It's a 2 by 4 matrix. What do you think the rank of this is? Well, it's at most 2, and it's certainly 2. If you apply the algorithm to it, you can stop right here. You don't need to compute the rest. You have 2 non-zero pivots, 1 and minus 4. And so the rank of this matrix is 2. Let's do an example where the matrix is tall instead of wide. So let's say we look at this matrix. Let's see, what do you think the rank of this matrix could be? It's either 1, 2, or 3. Well, you got to run the algorithm. You kill the 2, and you get this. And then you kill the 1, and you get this. And, well, you can kill that 2 down there, of course. And you see that the rank of this matrix is 2. And if you think about it, it couldn't possibly be 3. There's sort of no room for a third pivot there. In any event, we'll talk more about that, but the rank of this matrix is 2.